In the last lecture, we have introduced a special function that is an interesting function which has constant for positive t and another constant for negative t. Okay, here t is greater than 0 and this is positive constant, and here negative constant for t is less than 0. Let me denote this amplitude is going to be 1 and this amplitude is going to be minus 1. A function like this is defined as a Signum function, Signum, Signum function, and it is usually denoted by SGN, Signum, okay, in short form, Signum of t. So the definition is as follows: Sg of t is equal to positive value when t is greater than 0 and negative value minus 1 when t is less than 0. When exactly t equals 0, then what will happen? You take the average. What is the average? Here the value is 1 and here the value is minus 1. You take the average, 1 plus minus 1 divided by 2, which is 0. Therefore, if somebody asks what is the value at t equals 0, then you can say it is 0 for t equals 0. And such a function will have a time variation like this. Okay, this is called a Signum function. So obviously its Fourier transform can be derived in the usual way, and moreover if you look at this function, it is an odd function. So for odd function, if you take Fourier transform, it is purely imaginary. Okay, so now let us try to find the Fourier transform of this guy. Then let's say x of t is equal to Signum of t, then x of j omega is equal to x of t times e to the minus j omega t and dt, right? And the limit is minus infinity to plus infinity. Now minus infinity to 0, it takes the value of minus 1, and 0 to infinity, it takes the value of 1. So I can break this integration into two parts. So minus infinity to 0, in that range x of t values minus 1 times e to the minus j omega t dt, plus in the interval 0 to infinity, it takes the value plus 1 times e to the minus j omega t times dt. Now let me call this is I1 and this one is I2. My idea is to combine these two terms in some fashion and put them in the same limits of integration, like 0 to infinity. So for that, what I am going to do is put t equals minus tau, therefore dt is equal to minus d tau, right? When I am going to do the substitution in the first integral, I am not going to disturb the second integration. So consider only I1, because I want to write this I1 in terms of 0 to infinity in this limit, so that I can combine the first integration to second integration. So for that purpose, we will do this kind of substitution. Now when t equals when t goes minus infinity, then minus tau goes to minus infinity, that means tau goes to plus infinity. When t equals 0, which implies tau also goes to 0, right? Now therefore your I1 integration becomes integral of plus infinity to 0, then e to the t becomes minus, therefore j omega tau, right? J omega tau times minus d tau. So I take this minus in outside, integral of e to the j omega tau d tau, and the limit is infinity to 0. Now interchange the limit, then because of that you will get one more minus, so that minus and this already existing minus will become plus. So therefore 0 to infinity e to the j omega tau d tau, right. Therefore the first integration I can write as integral of 0 to infinity e to the j omega tau d tau plus integral of e to the minus j omega t and dt, and the limit is again 0 to infinity. So that is the whole idea of this substitution. Now after all, in this first integration, this tau is a dummy variable, right? You can put whatever the variable like it. So simply you change x tau to again t. Therefore then this is 0 to infinity e to the j omega t dt plus e to the minus j omega t dt, and the limit is again 0 to infinity. Now do the integration, it becomes e to the j omega t minus, by the way, one second, hold on. I missed out some minus symbol somewhere else, am I? Yeah, there is one more minus, I am sorry. Let me, yeah, there is one more minus, and this minus comes from the dt, and a change of limits brings one more minus. So there are three minus sign. So finally, see, this is the first minus sign, second minus sign due to d tau, this guy, second minus sign, and change of limit, third minus sign. So totally three minus signs, therefore you will have minus here. Okay, so this is minus, therefore minus e to the minus j omega t, then plus e to the minus j omega t, then multiplied by dt. Okay, so 0 to infinity e to the minus j omega t minus e to the plus j omega t times dt. Then if you simplify this, you will get a minus 2 times j times sin omega t dt, and the integral is 0 to infinity. Now this minus 2j you can take it outside, minus 2j 0 to infinity sin omega t times dt. What is this integration? By your distribution theory, this is going to be 1 over j omega, sorry, 1 over omega. So finally it is going to be minus 2 times j times over omega. This is 2 by j omega. Therefore Signum of t has a Fourier transform of 2 over j omega. This result is very, very important. Even we will use it in communication engineering also, especially when we talk about single sideband modulation in AM modulation. Okay, amplitude modulation, there is a variant called single sideband modulation. There we use this Signum function. Therefore we had when we had in the derivation of the unit step function, you recall that u of t is 1/2 plus half times Signum of t, right? So just apply this. Half is like this, 1 by 2, then another one is like this half, and this is minus half. Now what is the Fourier transform of this? This is 2 pi times del of omega, then 1 by 2 multiply, 1 by 2 times 2 pi times del of omega, 2 will get cancelled, therefore pi times del of omega. And here what will happen? See, Signum of f, you know, 2 by j omega, right? Signum of t is 2 by j omega, but here we have half times Signum of t, Therefore this is equal to 1 over 2 times 2 by j omega. This 2, that 2 will get cancelled. Therefore you will get 1 over j omega. So add these guys and that guy. Therefore this is equal to pi times del of omega plus 1 over j omega. So this is the same result that we derived for the Fourier transform of your unit step signal u of t. So a signum function can be represented in this fashion, and it has a Fourier transform. Previously it is 2 by j omega, but the signum function is multiplied by 1 half and here minus 1 for 1 half. Therefore this is 1 by 2 signum of t. Okay. Now let us take a truncated signal, sinusoid. Let us try to find out the Fourier transform of truncated sinusoid. Okay, if the sinusoid is truncated, then how do you find out the Fourier transform? So what we are really mean by this is, suppose you have a function which is only lasting for positive t. When I say sinusoid, the sinusoid is existing from minus infinity to plus infinity. It starts from minus infinity plus infinity. Now what I am going to consider, this is normal sinusoid. Now I would like to find out the truncated sinusoid. That means I will truncate from one particular point, and that signal I will allow to exist from that point onwards. So I have a waveform like this. So if you describe this guy, first guy, then it is going to be sine of some fundamental frequency omega naught. So this also same sine omega naught, but now this is multiplied by u of t. So that means it has one value only when t greater than 0. Therefore for negative values of time it is cut off. See, cut off. So this we are calling a truncated sinusoid. To find the Fourier transform for this, what will you do? You take cos omega ct multiplied by u of t. Now this you can write as 1 by 2 times e to the j omega ct and u of t plus 1 half e to the minus j omega ct and u of t. Okay. Now you know the Fourier transform of u of t. You can apply that and you can find the Fourier transform of this whole expression very easily. Okay. So how do you do that? We know that u of t Fourier transform is pi times del of omega plus 1 over j omega. Now I have omega ct. So if you multiply 1 half times u of t, what is the Fourier transform? You multiply 1 by 2 both side. So what is that? Pi by 2 del of omega plus 1 over 2j omega. So this is the Fourier transform of 1 by 2 u of t. Now this is multiplied by e to the j omega ct times 1 half u of t. So this has the Fourier transform of, if you multiply, you know the property, x of t has the Fourier transform of x of j omega, e to the j omega ct times x of t has the Fourier transform shifted by that amount omega c, j times omega minus omega c. So that property we are going to use it here. So therefore pi over 2 del of, instead of omega I have omega minus omega c plus 1 over 2j times omega minus omega c. That's it. Similarly, you can have the Fourier transform of e to the minus j omega ct 1 half u of t. Then this is going to be pi by 2 del of omega plus omega c plus 1 over 2j times omega plus omega c. That's it. Therefore, in the left hand side, what is this? If you add these two guys will yield cos omega ct times u of t, and the corresponding Fourier transform will be the summation of these 4 terms. So therefore this is going to be, you can take this pi is common, you can bring it outside, maybe 1 by 2 is common, you can bring it outside. Then del of omega minus omega c plus del of omega plus omega c plus 1 over j times omega minus omega c plus 1 over j times omega minus omega c. These all 4 terms. Again, if you simplify further, then it is here pi term is there and here also pi by 2 within the bracket del of omega minus omega c plus del of omega plus omega c. Then these 2 terms, if you further simplify, then it would be plus what you call j times omega divided by omega c squared minus omega squared. Again you multiply by 1 by 2. Okay, so the spectrum would be like this. At omega equals omega c and omega equals minus omega c, you have delta functions, 2 delta functions. Omega equal to minus omega c corresponds to this delta function. Omega equal to omega c corresponds to this delta function. In addition to these 2 delta functions, you have a continuous variation of the magnitude corresponding to this guy. Okay, omega divided by omega c minus omega square. So if you try to plot this, then it looks like something this. At omega c minus omega c, I have an impulse and the pulse width is pulse strength is pi by 2. At minus omega plus omega c, you have another impulse pi by 2, and now you have a magnitude plot like this. This corresponds to omega over omega squared over, I'm sorry, this is omega squared. Is it omega squared or omega? I don't know. Check this one. Okay, and here also it goes like this. It's a continuous magnitude. Like this. Okay, so you observe that we are not taking a pure cosine wave lasting from minus infinity to plus infinity. Okay, so if it had been a cosine wave lasting from minus infinity to plus infinity, only one single frequency term would be present. Okay, only omega c, if you recall. Okay, if you take Fourier transform of sin omega ct or cos omega ct, it has only one frequency component. But here we have, in addition to this single frequency omega c, we have many frequencies. Okay, it's a continuous spectrum. Therefore you would have spikes at omega equals omega c and omega equals minus omega c. Okay, so let me check the property result. Where is it? Sin omega naught t. It's very simple. Okay, so this is, you take LCM of this guy, so j times omega minus omega c plus j times, one is omega minus omega c and another one is omega plus omega c. Omega plus omega c divided by j square becomes minus 1, you put minus here, omega plus omega c, omega square minus omega c squared, that is correct. Okay, denominator. Okay, and the numerator j omega and plus j omega 2 times j omega, and minus omega c plus omega c will get cancelled. Therefore this expression is, this is not square, this is as it is, and this one is, there is no half, this half and that half will get cancelled. Therefore this is correct. So your final expression will be pi by 2 times del of omega minus omega c plus del of omega plus omega c, and the whole term is j omega divided by omega c square minus omega squared. So this is correct. Okay, so there is no 2 term here, that's it. Therefore, you would have spikes at omega equals omega c and omega equals minus omega c. So, this is not a pure cosine wave. Truncated cosine wave is not a pure sine wave. It is cut off for negative values of t. See, this region is cut off. Therefore, it is not a periodic phenomenon. But this guy is periodic. Therefore, you have other frequency component exist in this case. Not only the infinite coefficient density at omega equals omega c and omega equals minus omega c, if you look at the spectrum of this guy, plus the continuous band, see it continuously changing like this, continuous band of frequencies with various magnitudes. So, a pure cosine omega ct as such without multiplication by u of t, it would have been pure impulses. Suppose if you take cos omega ct, then it is a pure impulse, here one impulse and here one impulse. But if you take cos omega ct multiplied by u of t, then the spectrum looks like this. It has two impulses. In addition to that, it has continuous spectrum like this. Okay. So, in that lasting from minus infinity to plus infinity, you have an additional portion of the spectrum like this. These are the additional portion of the spectrum. Similarly, you can derive the spectrum for sin omega ct u of t, the same procedure. Okay. So, what you do, you take sin omega ct times u of t, you express this guy time as 1 over 2j times e to the j omega ct times u of t minus 1 over 2j e to the minus j omega ct, then u of t, then you take the Fourier transform of u of t, then multiply by 1 by 2j in the output, then you apply the time shifting property, then add all this, then you will get 4 terms in the output and combine the similar terms. So, it is fairly straightforward, pretty straightforward. Okay. So, let me stop at this point. In the next lecture, we will talk about a few more additional properties like convolution property, and if time permits, we will discuss integration property also. So, let me stop at this point. Thank you very much.